Okay, let me put this at the side. Yeah, so hi everyone again, and welcome back to the Generative AI Book Club. Last week we covered, let me just put this to the side. Last week we started the foundations of modern language modeling, and we spoke about the principles of tokenizations and positional encoding. And today we will cover pre-training recipes and distributed training and FSDPs. This concept would sort of like build on each other. So the concepts on pre-training recipes would build on some of the ideas that we discussed during tokenizations and the things we discussed during positional encoding. Again, I encourage everyone to go back and review prior slides because they're kind of sequential. The knowledge builds on each other. The slides for those are available on the book club genai GitHub. I think if you scroll down to slides for this presentation, you can find that. I believe my slides for last week were uploaded, so I think you can find them here. And I believe there are others for the others as well. I haven't pushed the slides for this one yet, so I think this is empty. Yeah, but after this class, I will push those on GitHub because last week I believe John merged my pull request, so which was great. So yeah, so those slides will be available, and also the recordings for most of the discussions that we've had so far are also available on the YouTube page for the DSLC. So if there's need to go back and revisit those concepts, definitely that's where to find them. Yeah, so that's what we will cover for today. We will be discussing pre-training recipes. I will try to go as fast as I can with some of the material, and then so that we can maybe have some time for discussion if need be. So so again, last week, so the purpose of this chapter, pre-training recipes, is to understand some of the fundamental choices that go into training, into pre-training models. So our main goals here is to understand effective pre-training choices and the scaling strategy. So it builds on the decoder-only transformers course, which was given by, I think we had a section on that earlier that was taught by David. So it's kind of discussed expanding on that. Then afterwards, we will, in the second part of this presentation, I will discuss a little bit about distributed training and how that works, talk a little bit about hardware requirements, GPU requirements, and things of that kind. And the overall goal here is to understand some of the foundational concepts that are necessary for understanding a large language model. So what is pre-training? Pre-training means teaching an LLM from scratch on a vast amount of text data. And the goal here is to predict the next word. The resulting model serves as a powerful starting point for more specialized tasks. So we can have more specialized AI agents that that we can build on. So we're building some sort of a base model that can later be fine-tuned to do more specific tasks. Again, invite you to revisit the section 2, which talks about, which I think David discussed a little bit about that, which kind of spoke a little bit about the fundamental principles around neural sequential prediction, and to really build on that knowledge moving onward. So the big picture here with pre-training here is a supervised task of predicting the next words or missing words. So it requires a a significant amount of resources. So when we make good choices, it helps to improve the model's general understanding of the language. So making sure that the data is appropriately or correctly labeled, I think helps to improve its capabilities. But also pre-training is very resource intensive because it requires significant compute. It requires a lot of data. It requires a lot of engineering and more especially safety engineering, which we haven't had a chance to discuss yet. Safety in AI models. So resources has been quite a major discussion. I think we have seen the scrambling for GPU chips. We've seen discussions, especially from NVIDIA, on how they are allocating resources for etc. So some sort of like an arms race for GPU chips is sort of what all the major players are right now, is really scrambling for GPU chips, because those are the most foundational hardware that's needed to scale. So it's very important, and the reason why they're all scrambling is because you definitely need a lot of compute to train this model. But aside from that, you also need to make the adequate design choices after, because they affect your training efficiency and the model quality, and that's what we will sort of discuss a little bit on. So we discussed about the transformer architecture. I discussed a little bit about, we showed a slide that showed an image in the previous slide presentation of foundational LLMs. We spoke about tokenization, this whole concept of turning text into modern readable tokens, almost like converting those texts into numerical values that a computer can easily understand. Then we discussed about positional encoding, which is about representing sequence information in a particular format. And I showed a slide, or an image slide, that showed how those sequential informations are being presented. So today we're going to mostly examine how to effectively train these models so that they become powerful and they become efficient. And there are four main decisions that are crucial when training large language model. The first is attention mechanisms, the activation functions, different normalizations, techniques, and then model sizing and dimensionality. And I think each choice here impacts the performance and the efficiency of the models. And I'll kind of briefly touch on each of these. And I remember last week I shared a paper on attention is all you need. I kind of encourage you all to read that. Really great paper that sort of set us on fire for all the innovations that we're currently seeing in the decoder only transformer models that have so far been released. So again, when it comes, I'm going to briefly touch on each of these choices: attention, activation functions, normalization approaches, model sizing, and dimensionality. So when it comes to attention mechanism variants, we have three main approach. We have the multi-head attention, which is the original, and it's the most expensive. It's the original transformer design, and has multiple attention heads, each with full query and query projections. It's the most expressive, but also computationally expressive. I think I might have an image somewhere that shows how a multi-head model typically looks like. Definitely more compute in order to have each of these in parallel, operate in parallel. So definitely multiple heads, each with a full query, full set of values, etc. We have the multi-query attention, where you have shared key, and then you have value projections across heads. So the queries remain separate, which reduces memory and bandwidth requirement. Then we have the group query attention, which kind of is a more balanced approach that sort of incorporates the MHA and the MQA. So the key values are shared among the groups of heads, and there's a better balance of efficiency and expressiveness. So there's not a one size fit all sort of recipe. Your decisions in architecture and training setup and data handling directly influence the performance and the cost and speed. So there's not so much, it really kind of depends. But one of the key things to keep in mind is what model architecture to go with and what sort of training setup to handle and how you want to have your data trained or structured. Then for the trade-offs, and here's how attention variance compare. As I said earlier, the multi-head attention is the most computationally, is the most expressive, but also the most computationally expensive. The MQA is kind of a little bit moderate. It's more memory efficient, and the GQA is sort of a trade-off between. It's sort of a more balanced model between the two. So the GQA, the group query attention methods, has been used or is currently being used by Cloud AI from Anthropic and also by Palm. But again, each of these models have their own advantages and disadvantages. You can see the MHA has the highest parameters, the MQA the lowest parameter. The MHA definitely requires the most memory compute, etc. So that's how all three of them vary. Then on a visual, just to show how these three methods or variants compare with each other, here we have the multi-head. Here we have the multi-head attention. You can see all the values are separate, the keys are separate, queries are separate. In the multi-query, you see that all the values and keys have sort of been combined into one, and then we have different queries. Then group query sort of uses a little bit of both, where you have different keys being combined into one. So that's how this impacts the expressiveness of the model. So this mainly is to compare the attention mechanisms, and you have to particularly pay attention to the memory savings versus the expressiveness of the MHA model. But the GQA model here is more of a balanced middle ground for comparison here. Then apart from the attention methods, we have different activation functions, and activation functions determine neuron activity in a model. So an example is that be able to think about how neurons typically fire in the human brain. So a good analogy here is think about it like how a typical neuron, would fire in the human brain. So it's the same with how that works in transformers. So we have activation functions that help to determine neuron activity within transformers, and we've evolved from the simple ReLU method to more smoother JLU method and more powerful SWICLU method. So the switch method, or the plus GLU combination, has been utilized in Llama and in Google Palm and other recent models. Computationally more expensive, but definitely produces really great results as well. Then here we have a slide that shows a comparison of the ReLU versus the GLU activation method. So you can see on the red line here, we have the straight line outputs 0 for negative numbers and increases linearly for positive numbers. The green light here is the silo or the switch, which kind of green blue. If you here we have the green light here and the blue line here. So the smooth curve that slightly dips below zero for negative numbers and then smoothly increases upwards. Then we have the LU, which is the purple line that you can see here that becomes slightly negative and smoothly for negative input, but rises sharply for positive, the positive ones. Then we have the sigmoid curve, and the sigmoid curve here, which looks like an S, as you can see, has the that outputs between 0 and 1, but often used for binary operations. So each activation function has unique behaviors that affects how the neural network learns. So the ReLU is the most simple and efficient, while with other functions like the switch or the silo or the switch and LU allow for more smoother gradients, which can help neural networks to learn better. Here's a mathematical computation that shows the characteristics of the Swiglu model, where the switch X here is the X here, or at least the multiplication here denotes the element-wise multiplication for the computation. The benefit of the Swiglu over others is it provides you with a more smoother or better gradient flow in the model, as I mentioned earlier, where the slightly dips below zero, then increases afterwards. More improved representational capacity, modest compute overhead for significant quality gains. So definitely very popular, has been used very widely. But I think the key point I just wanna to take away is the fact that the Swiglu combines the benefits of switch and gated linear units. It improves gradient flow and representational capacity, which offers notable performance boost. The third key concept I spoke about was normalization techniques. And normalization techniques, we have layer normalization, and then we have the RMSN norm. So the layer normalization is standard for stability, while the RMS norm simplifies computation and removes the mean centering step, which is increasingly popular in more recent models, and it's been used increasingly in the training of llama. So different techniques. So normalization here, we're trying to, our goal here is to stabilize the model across multiple dimensions. Then finally, we have optimization techniques or strategies. We have different optimizer choices. We have learning rate scheduling, we have weight decay, we have gradient skipping. For optimizations, we have the ADAM-W, which is a standard choice for LLMs. While I was preparing for this lecture, I actually learned that the guy will design this methods actually works for I think XAI or something. So be exciting to see what they what they might have in store in the next future, but kind of interesting. But the ADAM-W has become the standard optimizer. The other factor and Lion offer memory efficiency and simpler updates respectively, but for more specific use cases. But I think the ADAM-W has become pretty much standard. There's a huge, large paper I read on this. I think it's by Jimmy Barr. Is his name? Done really fantastic work building this optimizer model. So I think really great work for them there. Then we have different learning rate scheduling. So typical LLM learning rate schedule. We have the warm-up phase, we have the decay phase. So proper scheduling ensures stability. Typically, a warm-up phase prevents initial instability, followed by a cosine or linear decay phases for fine-tuning learning in general. So, and on this graph here, I was trying to find a graphic, something on the internet that can help to explain this learning rate decay concept. Kind of difficult, but the key here is to is to show how choosing the right learning rate impacts the training of neural networks. So when it's too when the learning, so on the y-axis here we have the loss, and then on the x-axis we have the learning rate. So when the learning is very slow, doesn't really start properly, the network doesn't improve that much. Then just right around the middle section, when the learning rate begins to go up or increase a little bit, then we begin to have losses begin to decrease quite a bit. And then you can see, around 10 minus 3, we have a significant decrease in loss as the learning rate increases. So small increase in loss you begin to see a learning rate becoming too large. So kind of have to find the right balance for learning in order to adjust. So I think the key takeaway here is to choose a learning rate that's neither too small nor too large, but that also ensures efficient and stable training of the model. So it's not a one size fits all, but to find one that could work for that could be most optimal to prevent minimal loss as possible. Then we have effective batch sizing, which here talks about balances memory and accuracy. Large batches offer stable gradient estimates, but have diminishing returns. So the right balance is always key. We want to kind of hit that sweet spot in the middle between memory and accuracy as well. Dropout strategies is to help us prevent overfitting. It's historically very common with modern large language models that use minimal dropout, focusing instead on increased training data. So it's been applied in attention output, feed-forward output, and embedding layers as well. Yeah. Then we have the training duration and data reuse as well when discussing pre-training. One pass, epoch is just having one pass through the entire data set. So modern models rarely complete full data passes, what I'm referring here as epoch. Instead, they are trained extensively with strategic reuse of high quality data to improve performance, because you can't really use everything. You have to have a kind of very, very, very good subset of data that has been correctly and robustly trained and labeled that improves the output. There's just no way to have like a complete full data pass. And I kind of feel like this concept will become increasingly more challenging as the internet becomes saturated with a lot of synthetic data, because there's just so much data we can have over on the internet. So I believe companies are envisioning how to innovate around that, because as people begin to use AI more and more, then we will get to a point where the internet is just saturated. I think a lot of articles that people are writing are mostly AI generated and things like that. So we might get to a point where the internet is sort of saturated. And I saw a nice paper in Nature that discussed about models collapsing when recursively trained on on AI generated content. I think it was a really fascinating paper which I read, I think about a year or two ago and stuff. And I thought I'll try to find the paper and I will drop it in the Slack channel for us all. That was a very interesting concept there. Yeah, there, like I said, you want to have a strategic reuse of high quality data to improve performance of the models. Some of the tokens that we've seen during training, we very, most of the companies are using huge amounts of training compute to train their data. Data comes from different sources and all that. Then talking about scaling laws, I think we will discuss more about scaling laws later on, but the chinchilla scaling laws teach us to balance model size and data volume to ensure optimal use of compute resources and effective training. Hyperparameter here, primarily discusses how to rely more on proven defaults rather than extensive tuning. So the focus mainly is on learning rates, weight decay, dimension, model dimensions, and different batch sizes. Some of the engineering considerations, which is the fourth concept that I was getting at, hinges on techniques like mixed precision, gradient checkpointing, model parallelism, data parallelism, zero redundancy optimizer, and then flash attention, which help to efficiently manage resources and accelerate training. But what are the industry best practices from recent trends that we've seen from most of the recent labs is most of them are using the GQA, which is the group query attention and Swiklow and the RMS norm architecture, and also large batch sizes and minimal dropout. So focusing heavily on careful data curation. Yes, and and then large amounts of token batch sizes, which aims to minimize dropouts and also better compute optimal training allocation, which would be useful for data curation and filtering. So some of the resources that I use here, again, I really encourage you all to review some of the material that has been put out by Andrej Pathy. I think he's been really fantastic. He has a really long video on tokenization and the use of the technical workings of large language models. You can find him on YouTube. He has some really exhaustive material on that. There's a book by the Novices LLM Training Guide. I also encourage you all to read that, Navigating Attention Landscape. I also encourage you to read a paper on Attention is All You Need, which I think laid out the foundations for most of this. So the key takeaway from this chapter is that many architectural training choices affect large language model performance. Modern defaults have emerged through industry experimentation, but I think as AI continues to expand and grow, we will see new and better architectural methods being implemented. We spoke about the importance of balancing compute efficiency and model quality, seeing those as crucial. Then both architecture and optimization strategy, they matter significantly, and there's no single best recipe. It really depends on how much resources you have and specifically what are the goals of the training. So that's it for chapter 15. I just really wanted to lay the foundation there on what are the requirements, what are the things that go into training this pre-training these large language models. I talked about the attention mechanisms. I spoke about the activation functions, talked about different ways to stabilize the models so they don't deviate from what they've been trained to do. Spoke a little bit about model sizing and dimensionality. I just noticed some of my slides, some of my images didn't render, so I'll have to go back and see what's going on there. But if that's okay, I will proceed with the next slide presentation, which chapter 16, which is on distributed training and FSDPs. Let me see if that will render there. Yes, that should, hopefully that works. Good.
Yes, thank you for that previous chapter. And I know that was a lot of material to summarize, and thank you for organizing it so well. And it is news to me, all the new activation functions and whatnot, and I'll look forward to reading more about it in the future. And now I'm looking forward to this next chapter.
Yeah, thanks a lot, Eric. Yeah, so the next chapter is on distributed training. So we've covered pre-training recipes, which is what I just covered, chapter 15. So we're going to learn a little bit more about how to scale LLM training. And again, the foundation or the goal of this is to explore how to scale up training of large language models using distributed training methods and focusing specifically on full-sharded data parallelism. So the problem with why is this important? Why does this matter? Modern large language models are they're extremely large, as you know, often have billions or trillions of parameters, as I had earlier shown. So that exceeds a single GPU capacity. So we try to distribute computation across multiple GPUs to overcome this limitation, which is what most of the GPU chips, especially those from NVIDIA, have been mostly optimized for different sorts of parallelisms within the model. Some of the hardware requirements for large language model. Here we see typical hardware setups for training large language models that illustrate the difference computational and memory requirements. You have the graphics processing units. We have central processing units, which many of you might be familiar with because that's how most of our previous computers have CPUs. Now we've sort of transitioned to this era of accelerated computing that's been driven mostly by all the innovations that have happened with GPUs or graphics processing units. Then we have memory, RAM, storage, networking, cooling, and power supply, and then distributed computing. So those are some of the foundational hardware requirements that typically go into LLM, large scale LLM training. Then GPU requirements, we have to, so here I'm just trying to illustrate the memory needs. Models quickly exceed the available GPU memory, which makes distributed solutions really essential. Here I found a formula for calculating how many GPUs might be needed, which here was equals to the total memory required divided by the memory per GPU. So a lot of computational resources goes into training most of these models. So it's an increase. Really depends on how many parameters you have, and lots of them have trillions and trillions of parameters. How many memory per parameter? Inferential compute, etc. So a large amount of computational resources goes into training most of these models. So you want to find the most efficient methodology for really to get the best out of to get the best output from your box. So parallelization is one of the strategies that are increasingly being used to ensure the most optimal output. So there are four main parallelism strategies. We have data parallelism, which is simple but limited. We have model parallelism, different layers on different devices. We have large models, but sequential processing. We have pipeline parallelism, and then we have tensor parallelism. So different ways of ensuring that these workflows work together. One of the easiest ways I've tried to explain this to others is our CPUs or our computers are not very good at doing things in parallel. That's why if you have many, I'm trying to think about websites that can be very computationally resourceful. Let's say YouTube, like you're playing 100 videos on different YouTube tabs and stuff, your computers begin to slow up because your computer doesn't have the capability to handle multiple tasks at the same time. So it kind of begins to slow down. But the difference with GPUs is the capability to essentially allow those different tabs to function in parallel without each of those affecting each other, without each of those workflows or each of the resources in each of those tabs affecting each other. So parallelism makes it more efficient to function. And I think that's what most of the GPUs have sort of been trained to, sort of been adapted to do or customized to do. So it really helps to efficiently split computations and make it a lot easier to build on those models. Then we have the full sharded and data parallelism. The fundamental concept here is that shard model parameters and parallelism significantly, like I said earlier, significantly accelerates training by distributing computations, balancing load, and improving throughput. And FDP parallelism divides the model into shards across GPUs, so reduces memory usage dramatically, and each GPU handles only a fraction of the total model efficiently using the resources. So that's one of the benefits of full sharded data parallelism, where you can lock different computations within clusters within the GPUs. And I think that helps to preserve computational efficiency of data parallelism. So that's what the full sharded data parallelism essentially entail. Here we have a sort of a visual that shows different layers. So it kind of helps to see how FSDPs distributes parameters across different GPUs. So helps to manage both memory and computation across different layers. It's sort of like in parallel without those affecting each other computationally. Then we have critical memory optimizations, which combine different techniques for maximum efficiency. We talk about mixed precision training, the ability to combine mixed precision training and activation checkpoints, and the accumulation greatly optimized memory usage during large language models. So different checkpoints that are essential to during the forward pass and the backward pass to trade computation for memory. So those are some of the practical implications or practical applications of this. I also saw this quote on when I was preparing for this lecture, which showed one of the implementation of the FSDP model for implementing FSDP, which helps initializing the processes, wrapping your model, and then training your model repeatedly in a batch sort of training training the model normally moving onwards. Yeah, so I think I can't really run this. I was thinking if I could anyway, maybe some other time. Here we're going to discuss about some of the hardware and computational and communication considerations that are important. Efficient training requires considering the hardware topology, optimizing communication to avoid bottlenecks, and different strategies for for hierarchical patterns and overlapping communication between overlapping communication with computation. So I already shared a slide prior, some of the hardwares that go into these LLMs. I think I shared a slide that showed the different tools and the different appliances and different strategies that sort of work in synergy in order to ensure that we have the best performance of this model, especially when it comes to parallelism. And parallelism here, I read about this 3D parallelism that combines data parallelism like the FSDP that I was just talking about, the pipeline parallelism, the model parallelism, and the tensor parallelism to scale up training massively, as it's currently being done by some of the leading large language model labs as well. So figuring out a way to build on that parallelism can help to optimize the outputs from most of these. So this visual I just picked out of the internet that showed some examples of how parallelism work, different pipelines, how the different structures are sort of layered with each other. That helps us to, so the goal, it really helps here to demonstrate the integration of all the different types of parallelism methods. That helps us to achieve very high and efficient large scale training overall. So different approaches here, different methods, different frameworks that are helpful. Some of the practical training challenges to talk about here, we have checkpoint management. We have the challenge with fault tolerance, performance debugging, and then different cost management here as well. The checkpoint, so the challenges at scale mostly include managing the mini checkpoints, the fault tolerance that might happen due to inevitable hardware failure. Sometimes, hardware may get bad or something might go wrong and then might need to be fixed or corrected. We have debugging some very complex interactions between the different strategies, sometimes that you have to pinpoint, identify, and then fix, then controlling the enormous training cost that happens. So there's so many things that could go wrong in a large language model that needs to be carefully monitored and accounted for. Otherwise, things can really ramshackle, but also controlling the enormous amount of training cost that goes into this. Yeah. And as I've said earlier, the training is not cheap, so GPUs are not cheap. So it's also kind of very important to have put that into consideration. And there are different frameworks that do exist. Talked about NVIDIA already, which is the Megatron LM. There's just so many different frameworks for parallelism that have been used, that are available out there. But the popular ones you hear about is, the native PyTorch, FSDP, the Megatron LM, etc. So there are many resources on this. I've put some of the links. It's also on the website. Yeah, so you'll probably find a lot on that as well. In the website, you can read more about each of these different techniques. The Megatron LM GitHub is available on the GitHub repository, so you can find more information on that as well online. So the key takeaway here is understanding that distributed training is essential for modern large language models. And the FSDP approach provides us with memory efficient data parallelism. It helps us to combine multiple parallelism strategies for the best results. Memory optimization is as important as compute scaling. Hardware topology should help to inform the parallelism strategy that we choose to take. Then large language model training represents extreme represents an extreme engineering challenge. I've spoke a lot already in the prior slides about some of the immense things that could go wrong, really, when training the model. But I think the most fundamental thing I wanted us to take away from this chapter is that distributed training is vital, absolutely vital for modern large language, and the FSDP, or the full sharded data parallelism, provides some memory efficiency and allows us to have more effective scaling, which requires combining parallelism strategies and memory optimizations that is informed by the hardware capabilities. So training large language models is a major engineering challenge, because you have to take all of these different elements into consideration when building and when building and also thinking about maintaining these different infrastructures. So there's a lot that goes into this, but I'm hoping that you at this point you have a better understanding of why distributed training is critical, why some of the GPU chips, for instance, the ones from NVIDIA, are particularly fine-tuned for parallelism and enabling us to process different computations in parallel without those affecting each other. So yeah, so that's it for my talk and presentation, and want to thank you all for listening. I think in the next sections, we will close on these foundations of large language model. That would be discussing a little bit about scaling and the mixture of experts. And then I think Derek will walk us through methods for fine-tuning large language model, which is a chapter that I'm absolutely looking forward to. Well, now that we've built the models, how do we fine-tune the models and ensure that they actually do what they've been trained to do? So that's what we'll be looking at next time. So I think that's it for now. Thanks a lot, Derek, and the rest for listening.
And yes, thank you again, Brian, for putting this all together. And again, for if anybody's watching the recording or whatnot, a lot of this information is only a few years old. It is quite new in my opinion, and to be able to absorb and express this has been quite an effort. And thank you again, Brian, for handling that.
Yeah, thanks a lot. Appreciate it.